friends, this is Dr. V. Sivanagaraju, Associate Professor, AC Department, IARE. Today we are going to discuss SSB modulation. So what is SSB? SSB is single sideband modulation. In previous we discussed double sideband, suppressor carrier and amplitude modulation. So amplitude modulation, another name is DSB FC, full carrier. In standard AM, we are sending both the sidebands and the carrier. Whereas in DSB-SE, we are going to suppress the carrier. But we are sending the two sidebands. Okay. So in this topic, we are dealing only with a single sideband. So the name is SSB modulation. So in this topic, we are going to discuss the frequency domain description and time domain description of SSB modulation. So what is SSB? When only one sideband is transmitted, the modulation is referred to as single sideband modulation. We are sending only one. Why? In standard AM and DSB-SE, wastage is the transmission bandwidth. Why? They are sending both the sidebands, upper sideband and a lower sideband. So this is a wastage of bandwidth, transmission bandwidth. So for perfect utilizing of the transmission bandwidth, we are going to eliminating one sideband, either upper or lower sideband. Why? Because both the sidebands have equal symmetry, virtue of with the FC, carrier frequency. So both carrying same information. So it is wastage of transmission bandwidth. We are eliminating one sideband. Okay. Therefore, we transmit information contained within M of T. We use to transmit only one sideband. Only one sideband. So the name is called SSB, single sideband modulation. Now the frequency domain description. So the frequency domain description of a SSB modulated wave depends on which sideband is transmitted. Why? We're having two sidebands. We can transmit either one. Either means one upper sideband or one lower sideband. But generally we are using upper sideband. So considering a message signal M of T with a spectrum of M of F limited to the band minus W less than or equal to F less than or equal to W. That means the bandwidth is minus W to W. So you can see this picture. In this picture, the first one is message signal M of T in the frequency domain. So we can call it as frequency spectrum. M of F, the spectrum of message signal, having the bandwidth minus W to W. In the B picture, we're having spectrum of DSB-SE, double sideband suppressed carrier, but having both the bands, upper sideband and lower sideband. Along the FC, one side is coming to the right hand side, you can call as USB, and the left hand side you can call as LSB. In the C picture, having only USB, upper sideband. So we are eliminating one band, that is LSB, lower sideband. So here you can say half of the transmission bandwidth is necessary for the transmission of SSB. That means the DSB, SC or standard AM utilizes 2 FM bandwidth. The bandwidth which is equal to 2 FM. But wherein SSB half, that is FM, we are transmitting only one sideband, either upper sideband or lower sideband. So the transmission bandwidth is reduces to half when compared with the standard AM or DSB-SC. So what are the advantages of this SSB? SSB required half the bandwidth required of AM and DSB-SC signals, what we discussed. Due to suppression of carrier and one sideband, power is saved. And another advantage is reduced interference of noise. This is due to the reduced bandwidth. So if bandwidth is reduced, we're having two advantages. One is power is saved, and another one is noise interference is also reduced. What are the disadvantages? The generation and reception of SSB signal is a complex process since carrier is absent. The SSB transmitter and receiver need to have an excellent frequency stability. And another disadvantage is this modulation. SSB modulation is expensive and highly complex to implement. So these are the disadvantages of SSB modulation. And what are the applications of this SSB? SSB transmission is used in the applications where the power saving is required in mobile systems. And another application, SSB is also used in applications in which the bandwidth requirements are low. So these are the applications of SSB. And now we are going to discuss the SSB in time domain and description. Okay. So generally the SSB signal may be generated by passing a DSB SC modulated wave through a bandpass filter of transfer function HU of F. Why? The DSB SC double sideband suppressor carrier having two sidebands. Our aim is we're sending only one sideband and another band is going to element. So we're sending DSB SC double sideband suppressor carrier through a bandpass filter. It can stop one band and allows another band. That means only single band comes out of from the bandpass filter. So we can generate SSB signal. Okay. So the DSB-SC modulated wave is defined mathematically as DSB-SC of T, that is a modulated wave of DSB-SC, which is equal to the product of message signal and the carrier signal. So C of T is the carrier signal, which is equal to AC cos 2 pi FCT, and M of T is the message signal. So this is our DSB-SC. Now we are sending this DSB-SC through a bandpass filter. So the low pass complex envelope of the DSB-SC modulated wave is given by as tilde of DSB-SC of T, which is equal to AC M of T. So this is the complex envelope of the DSB-SC. Already in the previous expression, we see that DSBSC. What is DSBSC? It's just a product of carrier signal and message signal. So here low pass complex envelope of this DSBSC. So here we taken the separation of the complex envelope taken as upon the S is tilde S tilde DSBSC of T, which is equal to AC M of T. So consider the SSB modulated wave SU of T. Here SU of T indicates only one band, that is upper side band is retained. It has a quadrature as well as a phase component. Okay. So let the low pass signal S till U of T denote the complex envelope of SU of T. So we may then write SU of T, which is equal to the real part of S till U of T exponential J2 pi FC of T. Okay, so here we're taking the real part of this complex envelope of SU of T. Okay, so this is the frequency spectrum of the bandpass filter HU of F. HU of F. This is the bandpass filter. This is the low pass filter frequency response, and the filter is H till U of F. HU of F is the bandpass filter response, and H till U of F is a low pass filter response. So to determine S till U of T, the bandpass filter of transfer function HU of F is replaced by an equivalent LPF of transfer function H tilde U of F. We may express H tilde U of F as follows. That is H tilde U of F, which is equal to half of 1 plus signum of F. So SGN of is the signum function, and which is the range of 0 to W1. Otherwise, this is 0. Otherwise, it is 0. So now the DSB-SC modulated wave is replaced by its complex envelope. The spectrum of this envelope is S tilde DSB-SC of F. Already we turn S DSB-SC of T. S tilde DSB-SC of T, which is equal to AC M of T cos 2 pi FCT. Now this is sent to the low pass filter, and we get this frequency response of this DSB-SC of complex. So we taken as S tilde DSB-SC of F, which is equal to AC M of F. The spectrum is given below. Here AC M of 0. Why at F is 0? It is 0. M of 0. At 0 point of frequency, here taken the response of the message signal and the spectrum of that message signal, M of 0. Now the desired complex envelope S tilde U of T is determined by evaluating the inverse Fourier transform of the product H tilde U of F and S tilde DSB-SC of F. That is S tilde U of T, which is inverse Fourier transform of H tilde U of F, and S tilde DSB-SC of F. So S tilde U of T is the desired complex envelope. Desired complex envelope. So how to get? Just inverse Fourier transform of two responses. One is the low pass filter response and another is the complex of DSBS. So we are going to substitute equation 2 and equation 3 and equation 4. Already written what is H tilde U of F, that is half of 1 plus signum function of F. So another DSBSC, that is ACM of F. So we are going to substitute those two equations and two expressions and applying inverse Fourier transform, you get S tilde U of t, which is equal to AC by 2 of M of t plus J M cap of t. This cap is coming to the complex envelope, but taken as a tilde function. So by applying inverse Fourier transform, this is converted into the M cap. And substituting this equation 5 in the first equation first to get SU of t. So SU of t, which is equal to AC by 2 of M of t cos 2 pi FCT minus M cap of t sin 2 pi FCT. What is SU of t? Is a real part of that complex conjugate. We're taking the real part of this complex envelope of DSBSCC. So finally we got SU of t. There is a single sideband with upper sideband. We taken the single sideband is means upper sideband is retained. So SU of t is indicated. If you take any lower sideband, it changes as SL of t. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.